In this video, I wanted to look at the limits of a piecewise function, specifically one where there is a break discontinuity. So just revisiting the idea of a piecewise function is often written using a brace where basically there are two different or three or more different formulas which are separate the function based on the domain. So what this one is saying is let h of x be equal to 2x plus 2. There's actually a typo in your packet, so go ahead and fix this if you're working on it. But let's say we're looking at 2x plus 2 when x is less than 1, which would be a linear function, intercept of 2, slope of 2, which would look something like that. But when x is greater than or equal to 1, we're going to use this other formula instead. So at that point, we're going to switch over to the formula 2x minus 4, which would have an intercept of minus 4 should it continue there, and again has a slope of 2. So we can see these, and these would end up being parallel lines, but since it's a function, it's kind of split into two parts and still satisfies that vertical line test. So anyways, this causes a break. Basically, if we're imagining walking along our function, we have a nice continuous straight line, and at some point it just jumps to a new point, continues with the same slope. So let's examine some limits for this piecewise function. So let's say we're looking at the limit towards 1. 1 is kind of an interesting position on this function because it is the point at which the domain, we're going to swap from using one to the other, or kind of switch, as I like to call it with piecewise functions. It's like switches from this one to this one. So like looking at it from the left-hand side, and I mean, I can tell I'm going to be using this formula numerically speaking because when x is smaller than 1, which is what this means, I'm approaching it on the left-hand side, I'm going to be plugging into here. So I could always try to figure this out numerically by plugging in, say, 0.99 or 0.999, values that get closer and closer to 1 from the left. And actually, another thing I wanted to mention is it's very easy to accidentally think of this as a negative number. But remember, when you have a little negative up there, this is still a positive number. It would just be from the left-hand side. So if we were to look at it on the negative side, we'd write it this way: -1 from the left, -1 from the right. And it's important to recognize that distinction. But anyways, looking at the graph is easy here because we have the graph. But if I'm looking at the limit, well, what's the limit on the left-hand side of 1? It's clearly approaching that value, that point of 4, which would be kind of like the end point. But if you plug in 0.99 or 0.999, you'll see it will be very close to 4. Now, if I'm looking at this function from the right-hand side, this is going to be different because in this function, if I'm using values greater than or equal to 1, I'm going to be using this formula instead, and so I would have different numbers and it's going to be a whole different result. Like and again, I would plug in, say, 1.01, 1.001 because I need to be to the right of 1 and again sufficiently close. And what you'll see here is it will get closer and closer to the value of -2, but again, looking at the graph, much easier. That limit will be -2. And so our conclusion is the general limit towards 1. Which one is it? Remember, if they're not in agreement, we would say that this does not exist. And often in your homework, that would be an option. You probably don't want to just type in DNE unless it specifically instructs you to, because again, as I said, that's not proper notation, but it's good enough for communicating our meaning in this case. Now, let's say we're looking at a different point of the limit, like just any other point on the curve. Let's just say we're looking at what about -1, and we wanted to see that instead. So let me erase all this. Again, we could draw a wall through -1 if that helps us get started. Oops, I closed my tablet on accident. And I've completely lost my, there we go. Again, we could think about the wall. Wow, that's really fat. I didn't mean for it to be that fat. And do that. How do I make this more narrow? I don't know how to make this more narrow. So I'll just do this instead. You could always draw a wall here. And again, think about what's happening to the left of the wall and what's happening to the right of the wall. So the left-hand side, it appears to be headed towards 0. The right-hand side also appears to be headed towards 0. So left-hand limit 0, right-hand limit 0. And our conclusion is those are both the same. So that limit would indeed be 0 because we have the same thing on both sides. Or again, this would be called figuring out a limit by direct substitution. Since -1 falls within this interval, I can just plug it into the function, assuming it works. And since that function is just 2x plus 2, I could just plug in 2 times -1 plus 2, because that's where I care about the limit. In this case, it's a line, it's a continuous curve other than the point of the break. And this would be -2 plus 2, which is 0. And we could solve via direct substitution. That's sometimes what we call an algebraic method number 3. But again, those sort of methods are a little bit more confusing with piecewise functions. And my summary here is, when you have this jump in the function, you want to check both sides to see, does the limit match up? And one of the ways we define continuity is having limits which exist. And the fact that this limit does not exist mathematically indicates the break or the discontinuity in this function, whereas it is continuous along paths where the limits exist.